What's up, guys? It's time to start gaining security awareness when working with substrate-based blockchains and more specifically with Rust language. So whether you are developing smart contracts or auditing them, this is for you. And today it's going to be this way. I wrote this article a few weeks back, the top 10 vulnerabilities in substrate-based blockchain using Rust. And it will go through these vulnerabilities that we see here: insufficient benchmarking, unsafe arithmetic, replay issues, outdated grades. And yeah, the idea is to guide you through these vulnerabilities, explain why they're risky, showcase the impact they might have, and show you to mitigate them. And as you can see an example, because this can be a bit complex, I also decided to add some part with analogies, but for each of them there will be the impact, description there, and mitigation with the example, right? How to add it and what is done in each of them. Here the Rust level is a bit higher, so I'm not going to get into the code itself. I'm not going to go and explain every detail because it might get even much more complex. However, it is going to be very beneficial to just analyze it, to see how those are fixed, and let's say I will start getting familiar with it. And of course, if you're already more into security in Rust, then I'm sure having these examples here and access to this, it's going to be beneficial. Also, first of all, I wanted to say that this article I wrote, it's based on this list that it was created on Polka.forum, where they shortly describe some of the description. Let me stop. Okay, where they describe a bit of these vulnerabilities. However, since I was not confident that I understood these things when I was reading them, I decided to extend it. I decided to explain it in a different way, and basically, yeah, to try to get me and everyone else more aware of them. So let's start. Yeah, the first one is Insecure Randomness. I'm wondering if many of you come, or any of you comes from Solidity. You can let me know also in the comments and let me know if you found this type of video useful and so on, so that way I know what to focus on, because it can be either more focused on Rust development, or we can just also focus a lot on vulnerabilities in Rust. So yeah, let's start. So for insecure randomness, this arises from reliance on weak or predictable randomness sources, which could potentially be manipulated or anticipated by malicious actors. Here in Rust, we have this randomness collective flip palette, which is, I want to go through this first because it's the insecure approach. And this one utilizes the hashes of the previous 81 blocks to generate random value. And when you want to use this in Rust, this is how it looks. So basically you are adding those some of that logic on these functions on initialize and random. So here let me put it this way. The onInitialize function updates a storage item, the random material, with the parent block's hash at each block, cycling through the list of stored hashes. And the random function then derives a random value from a combination of the block number, a subject input, and the hash series. Now, what's the impact? Why is it insecure? This is particularly risky in applications like lotteries or voting systems on the blockchain, where in the integrity and unpredictability of random numbers are crucial. This approach shown above is less secure, because the randomness is directly influenced by past block hashes, which could potentially be manipulated or anticipated. Some of us that come from Solidity already are aware of this, and there are in Solidity it is sometimes used chainlink options that there are some libraries, and let's see how it is in Rust and what it's used to mitigate it. So here instead we use the verifiable random function from the Pale-Babe, and that's like let's say a bit similar to a library from Solidity. And yeah, what is it about? This Pale-Babe employs a verifiable random function to generate random values. The VRFs are cryptographic primitives that provide verifiable random outputs, which are difficult for adversaries to predict or influence. The randomness generated through this method is thus more secure and robust against manipulative actions. This is how it looks, the implementation. So basically it's about grabbing that logic and implementing it in, or using it in your contract in order to generate that randomness. So let's say a bit more about it. So the compute randomness function aggregates the randomness from the last epoch, the epoch index, and the iterator of VRF outputs from the prior epoch to compute new randomness. And then the randomness change epoch function is called once every epoch changes to update the randomness utilizing the compute randomness function. Let's go with the next vulnerability, storage exhaustion. Alright, so what it is and when does it occur? So it occurs when inadequate charging for storage use facilities malicious exploitation, slowing down the system and escalating operational costs. And here we have the example with this small contract with the implementation. And yeah, here's where we start with the simplified explanation, because when I was reading this description, it was a bit like, okay, so yeah, let's see an analogy. So let's imagine a public storage facility with very cheap rental rates. Soon, a person realizes they can rent out a large portion of the units at a low cost. They start hoarding, filling up unit after unit with junk, making it difficult for others to find available units. Over time, the facility gets crowded, and the management has to spend more on maintenance. Well, in this analogy, the storage facility is the blockchain. The cheap rental rate is the low storage cost, and the hoarder is the attacker, and the junk represents useless data, bloating the storage, which slows down the system and raises operational costs. And what's the impact? Well, attackers can exploit low storage costs to bloat the storage, making the system sluggish and expensive to maintain. How to mitigate it? So implement checks to ensure the cost charged to users is proportional to the storage used, and consider setting limits on the amount of data that can be saved to storage to prevent abuse. Now let's see how will our contract look with the advised mitigation. So let's see, because this is what I'm saying, like they would provide in the forum the mitigation, but again I had to figure out what it's saying here, how to understand it. So I wanted to extend it so I can add a few points, even though I'm not an expert on Rust at the moment at least. But yeah, let's see a bit about it. Okay, so what have we done to mitigate it? Let me have this. Yeah, so we added the cost per byte field. We can see, yeah, a new field. The cost per byte was introduced to storage contract struct to store the cost per byte of storage. Then it's we modified the constructor. So the constructor new now accepts cost per byte as a parameter, allowing you to set the cost per byte during contract creation. And then we update store data function. Let me highlight it. In the store data function, the storage cost is now calculated using this data.len as balance times self cost per byte, instead of just the data.len function as balance, utilizing the cost per byte field to determine the storage cost. So we're adding it and then we're using it here. Okay, let's remove it. And let's jump to the next vulnerability, unbounded decoding. What it is. So this vulnerability in Polkadot Substrate arises when there's no depth limit set for decoding objects like calls, extrinsics, allowing attackers to craft highly nested calls that the system struggles to decode, leading to a stack overflow. This is the way we would recognize it in the code. Okay, so let's see the analogy to try to understand this explanation. Now imagine a city road system as the network. Normally the cars or data flow smoothly. Now imagine a truck, so like a malicious crafted data with an excessive load tries to pass under a low bridge, or the decoding function, but it gets stuck because it's too tall, too deeply nested. This causes a traffic jam or stack overflow. That's what we could find the analogy with. The traffic jam blocking all cars behind it from moving or preventing that validators from generating new blocks, and over time the entire city's traffic or the network comes to a halt because of this blockage, and the depth limit acts like a height restriction on the bridge, ensuring only trucks or data of a manageable size can pass through, the keeping traffic flowing smoothly. And this is a kind of already the mitigation. Let's see first what's the impact. So a stack overflow with highly nested calls can disrupt the network's operation, possibly preventing validators from generating new blocks and halting the network. It seems like a kind of DOS attack also. And the mitigation. So to mitigate this vulnerability, it's advisable to set a depth limit for decoding objects. And this can be done by substituting the decode method with a decode with depth limit method in the code, ensuring that the decoding process doesn't exceed a certain depth and preventing then stack overflows. Let's see, this is where it's used. Instead, this is in the let call. So instead of being used the decode alone, then we can use the mention function. So in this modified code, the max depth is a constant that defines the maximum decoding depth allowed, providing a guard against stack overflow caused by excessive nested calls. Okay, so let's move further. Next vulnerability, insufficient benchmarking. What is it? It arises when an extrinsic, which is a type of function call in Substrate, does not have accurate benchmarking. And benchmarks help in understanding the computational and storage costs of executing an extrinsic. This is how the code would look, the vulnerability. So in this code, the weight is being calculated without considering the size of the remark vector, which means the weight could be underestimated. The weight, here. So let's see the impact. Incorrect benchmarking can slow down the network and allow attackers to spam the system by continuously calling under benchmarked extrinsics at lower than actual costs. Let's go through the analogy to see if we can also understand it in a different way, or with the help of an analogy. So imagine a public bus with a fixed ticket price, regardless of the distance traveled. Now, if a group of people start taking long distance rides frequently, the fuel cost for the bus company increases, but the ticket revenue remains the same. In the code scenario, think of the bus as the network, the ticket price as the benchmark weight, and the group of people as attackers. If the ticket price or the weight doesn't accurately reflect the cost of the trip, the execution cost, it could lead to financial loss for the bus company or the network slowdown or spam, and hence, ticket prices should be set accurately for different distances, much like how benchmarks should accurately reflect the computational cost for different extrinsic inputs. How to mitigate it? Perform benchmarks using worst-case scenarios condition to ensure accurate weight calculation as demonstrated in the provided code snippet below. This practice helps in better understanding and accounting for the execution cost, thus preventing potential spamming and slowdown of the network. So just in this case, it's just we need to consider, like if we would be reviewing them, or at least what I would understand it is that if I am auditing some contract with Rust, I would come across this implementation, I would be able to notice that vulnerability, and we know that there is a mitigation, there is a code we need or we can replace it with. Let's move on. XCM arbitrary execution. Let's see what is it. XCM arbitrary execution vulnerability arises in Polka.substrate when this XCM is the cross-consensus messaging is improperly configured, potentially allowing attackers to interfere with the system or perform unauthorized actions. Let's see. We have here the struct in the implementation, so like the start of the contract for config. And here everything is set as the safe call filter, which essentially allows all calls to go through without any filtering. What's the impact then? Attackers could exploit this vulnerability to execute any transacting instruction, possibly leading to unauthorized actions or system disruptions. Okay, let's see the analogy. Let's try to simplify this explanation. So imagine a building with a high security door, but someone left it set to let anyone in mode. So in Polkadot, this cross-consensus messaging is like that door, controlling who can send messages or transactions. So if not set up correctly, it's like leaving the door open, allowing anyone, including malicious actors, to send messages or transactions that could harm the system. By adjusting the settings on the door, so modifying the XCM configuration, like setting up a guest list or the safe call filter, you ensure only authorized individuals or approved calls can enter, keeping the building or the system secure. How to mitigate it then? So limiting the usage of XCM execute and send operations can mitigate this issue. Specifically, changing the everything value to a more detailed safe call filter, as shown in the provided code, can filter undesired calls, enhancing the system security. Let's continue. So XCM does, what is it? So cross-consensus messaging, denial of service. This vulnerability arises when inadequate XCM setup allows attackers to overload the system by spamming XCM messages to other chains. Let's see how to recognize it. We can see this handle XCM message function and that there is no validation of incoming messages. Okay, so here the handle XCM message, the function represents a simplified vulnerable XCM handler that processes every incoming message without validation. Then what's the impact? Attackers exploiting this vulnerability can cause a bottleneck in the XCM queues of the receiving chain, potentially stopping it from processing new messages or even dropping incoming messages, thereby disrupting the network's functionality. Okay, let's see the analogy. Imagine you own a small post office and you accept packages from anyone to deliver. Now, suppose a malicious person decides to overload your post office by sending in, an enormous number of packages at once. So many that you can't even move inside the post office. Okay, that's a lot of packages. This scenario is similar to the XCM DOS vulnerability, where an attacker spams a blockchain with so many messages that the system can't handle it, causing a backlog or even halting the processing of new messages. It's like a traffic jam in the network, preventing normal operations. So how to mitigate it? Properly setting up XCM to filter incoming calls and allow interactions only with trusted parachains that can mitigate this issue. Preventing those attacks by blocking malicious or spammy XCM messages from untrusted sources. And here is the implementation. And we can see we added condition to filter them before processing the messages. Okay, let's continue with Unsafe Arithmetic. And here I wanted to point out that Rust does provide protection against overflow and underflow in arithmetic operations by default. And when compiling in debug mode, debug mode, arithmetic operations will panic crash on overflow or underflow. And in release mode, Rust will perform wrapping arithmetic, where values wrap around on overflow or underflow. However, in Polkadot and other blockchain frameworks, arithmetic is often used to handle critical operations like token transfers, so the default behavior might not be desired. So unsafe arithmetic vulnerability in Polkadot and Substrate blockchains arises when the potential overflows or underflows in mathematical operations, which can lead to incorrect calculation results. This might occur when unsafe math operations are used in the code, which do not handle these cases properly. We have here an example of a transfer function with unsafe arithmetic that can lead to overflow, so we have the operations here. So let's consider this simple token transfer function above in Polkadot smart contract, and in the function directly subtract the transfer amount from the sender's balance and adds it to the receiver's balance without any checks. So an overflow or underflow error might occur, as I pointed here. So what's the impact? Attackers can exploit this vulnerability to manipulate the system, causing serious inconsistencies. For instance, in token transfer scenarios, it could lead to incorrect account balances, enabling attackers to gain unauthorized assets. Now, how to mitigate it with Rust? Utilizing safe math functions like check_add or check_sub, which check for arithmetic errors, is advised to mitigate, and it's advised to mitigate this issue. Thoroughly reviewing the code for unsafe math operations and replacing them with safe alternatives will significantly reduce the risk associated with this vulnerability. And yeah, here is how to mitigate the code that we saw above. So basically we need to use the checked arithmetic to prevent overflow and underflow. Instead of just subtracting or adding, we are using the mention function. Okay, unsafe conversion vulnerability. This occurs when converting one numerical type to another without adequate checks, potentially causing errors that attackers could exploit. Okay, we have an example here with this execute function, and yeah, let's see. So as you can see, it is using the low U64, and as we can see, possible overflow, to downcast the gas limit variable so as to be able to use in the runner call method. However, this method can lead to overflows as mentioned. So as the impact, errors from unsafe conversions could lead to overflows or incorrect values, which attackers might leverage to induce inconsistencies or undesirable behavior in the system. Now, how to mitigate it then? Ensure proper checks during type conversion, avoid downcasting, and utilize safe conversion methods like unique saturated into function. Reviewing the code for unsafe conversions and rectifying them is crucial for preventing this vulnerability. As you can see, this is how we can mitigate it. This is what we need to use instead. Instead from the gas limit that we did this with low U64, then we should be aware of this function for mitigating overflows. Let's go now for replay issues vulnerability, which arises from improper handling of transaction nonces, which could potentially allow attackers to repeat transactions and slow down the system. Okay, let's see. Here's how a simplified ink smart contract with a vulnerability to replay issues may look. I remember I generated this. I tried to replicate such a contract. So let's see what's the impact of it. The attackers exploiting this vulnerability can repeat transactions, causing network congestion and possibly leading to slowed or halted network operations. Now, how to mitigate it? Ensuring nonces are correctly set up in the system logic and implementing checks to prevent transactions repetition can mitigate this vulnerability. So for instance, in the frontier security issue, transaction validation or nonces were added to the state transition function or STF to prevent replay attacks. Now let's make a parenthesis here because Frontier is a substrate palette for Ethereum compatibility, and the state transition function or STF is crucial in validating transactions while blocks are being created. So by reintroducing transaction validation, specifically checking nonces, which are unique values associated with transactions, into the STF, the system can ensure that transactions are valid and haven't been submitted before, thus preventing replay attacks where a malicious actor might try to resubmit the same transaction to the network to cause disruptions or exploit the system. Now, to mitigate the replay issues from the code shown above, you would need to add a nonce verification step in the process transaction function to ensure that a transaction with the given transaction ID hasn't been executed before. And here's how you could modify the code. Let's see, we are checking for the transaction. Yeah, we added to the, so we can see here, transaction ID, we are verifying. So in the process transaction function, checks if a transaction with the given transaction ID has already been executed by looking up execute transactions. If it finds the transaction has already been executed, it returns an error. Otherwise, it proceeds to process the transaction and emit an event. Okay, next, outdated crates vulnerability. This arises when outdated, unsafe, or incompatible versions of dependencies or crates in Rust are used. This inconsistency can expose the system to known vulnerabilities and incompatibility issues. Now, the following palette uses dependencies from different versions of Substrate, and this could lead to serious incompatible problems. Here we can see it's an example of these dependencies. So yeah, what's the impact? Attackers could exploit known weaknesses in outdated crates to compromise the system. Moreover, inconsistent versioning across dependencies can lead to incompatibility problems, causing system malfunctions or unexpected behavior. Another parenthesis here to explain a bit more about crates. So crates are packages in Rust programming language. They can be libraries or binaries, executables, and crates can be shared on crates.io, which is the official Rust package registry. Or they can be private code that you use in your own projects. Each crate has its own local namespace and can optionally export some of its types, functions, etc. into a public interface. Now, how to mitigate it then? Always use the newest and safest versions of dependencies, ensuring consistent versioning across all crates. Keep track of any new risks and fixes, updating the dependencies accordingly to maintain system security and functionality. In order to fix the cargo.tom file above, all the Substrate dependencies should, for instance, be aligned to the same version. In this case, could be Polkadot version 1.0.0, which should help mitigate the risk associated with outdated or incompatible crates. Alright, let's go to the last vulnerability of the list, verbosity issues. So verbosity issues concern the lack of detailed logs from collators, nodes, or RPC in a Polkadot Substrate network, making it challenging to diagnose issues when anomalies like crashes or network halts occur. Here a simplified example illustrating verbosity issue. And in this contract, the setValue method updates the value state variable but doesn't provide any logging. The impact here is that insufficient logging can significantly delay the identification and resolution of issues, particularly during critical incidents like a network halt, causing extended downtime and resource drain. How to mitigate it? While implementing comprehensive logging in critical parts of your palette and regularly reviewing these logs for suspicious activity can mitigate this vulnerability. Ensuring adequate verbosity will expedite the troubleshooting process, reducing downtime. So to mitigate verbosity issues, you could add an event to log the change. And now with the value change event, let's see, you have logging in place to track changes to the value state variable, which would help in diagnosing issues related to value changes. And guys, that is all for now. This is an overview of potential vulnerabilities. I hope you found this useful. For me, it was interesting because I come from Solidity, and it was interesting to see that there are different type of issues because it has nothing to do with what we see in Solidity. However, there are also some DOS attacks or arithmetic overflows and so on that are also similar. And here we can see clearly how to find them or how to locate them in the code, and clear mitigation. Actually, you can use this code and add it there, and it is easy to provide when in an audit, private audit, or whenever you want to help someone with it. So let me know in the comment, guys, if you actually like this approach. Actually, this was a complex article, complex video. That's why I decided to go through the article. So let me know if this is annoying that I go through the article, or you prefer some fancy screens and screenshots and so on. But yeah, I think it's still useful, so I wanted to go through it. And if you stayed this long, then thanks for watching. Again, as always, consider subscribing. And if not yet, then at least support me with a like in this video. And yes, see you next time. Take care.